O. Romer defined freezing to be 7.5 and boiling 60, as we've seen. And then he established experimentally that body temperature would be 22.5 on his scale. Based on the Fahrenheit scale with freezing at 32 degrees Fahrenheit, boiling at 212 degrees Fahrenheit, and a measured human body temperature of 98.6 degrees Fahrenheit, what should Romer's value for body temperature have been? So the idea, what we're looking at here, is it turns out Romer was not entirely accurate when he established this 22.5. And we're going to investigate that based on these more modern accepted numbers. Now, you may know that 98.6 is not no longer maybe regarded as the like normal healthy body temperature that every single human being is always at when they're healthy, but it is the modern established value that most of us still look at. So that's the one that we're going to use, and definitely the 32 degrees and the 212 are well established. But what we're going to find out is if you convert 98.6 degrees Fahrenheit into a number in this Romer scale, which I'm just going to report as a pure number since this scale did not survive the test of time and is no longer an established temperature scale. It's kind of an anachronistic question in that sense. I'm just going to write down what number and see that it's not the same as 22.5, and then maybe we can look at like, well, what ramifications does that have in the next example perhaps. But let's see how should we do that. And I think the thing to appreciate is all temperature scales are related to each other in a linear way. So since I'm going to be looking at finding a Romer value from a Fahrenheit, I think I'm going to, like I did in the last example, I'm going to define a y variable and an x variable to represent these two. So I'm taking a very mathematical approach. I'm using notation more from a math class maybe than from a physics class, because like we've seen on the key concepts page that maybe I would call this t sub f, not an x, right? But it's easier for me, given the way this problem is posed, I think, to look at it that way. And in that sense, we can establish a slope based on the numbers that are here, and then kind of taking the point of view that those represent ordered pairs. So a slope should be change in y's over change in x. So in this case, maybe that would be 60 minus 7.5 divided by 212 minus 32, which is really going to be 52.5 divided by 180. So that's something I'll be able to use. And then we'll use that point slope form of a line to establish the formula, right? Recall that that was y is equal to m times x minus x naught plus 1. Let me make that y a little bit better looking. Sometimes my y's don't turn out perfect on the technology I'm using, but there it is, y naught. Hopefully that's good enough. So in this case, that would look like 52.5 over 180 times, and let's see, for the x naught and the y naught, I get to choose, like I can look at these ordered pairs here and pick which one I'm going to use. I liked smaller numbers, so I'm going to go with that one. In this case, the x naught would correspond to this 32, since we're establishing the x variable as corresponding to Fahrenheit numbers, so that'll be a 32, and then y naught will be the corresponding number in the Romer scale, so that'll be 7.5, which means that if I want to calculate what temperature this is at 98.6, I'm going to just say, well, let's let x is equal to 98.6, and then that's going to imply that y would be equal to the expression, 52.5 over 180 multiply. This one gets a little more complicated. That should be a 98.6 minus 32, and then close the parenthesis, plus 7.5, and that's a whole lot of calculations. So I'm going to go look in my calculator, and I get the result of 26.925. And I think the philosophy I've taken with these examples is I haven't worried about significant figures, because I've been kind of doing this in this very math kind of way, and since mathematicians often don't round off or worry about sig figs and measurement errors, I'm just going to take that philosophy and not worry about rounding. Just say that that's my answer to this very mathematically posed question.